Hello. So in this video, we're going to start looking at section 2.3 of Haberman. And the goal is to systematically generate, produce, compute, however you want to say it, solutions to kind of a problem of this form. So the PDE we're looking at is a heat equation where everything's all the coefficients, C, rho, and K naught are constant. We don't have any source. Our boundary conditions are 0 physically, right? We're saying temperature has to be 0 at the boundaries. And then some initial condition given by an initial temperature profile, f of x. Okay. So we're going to produce solutions to this problem. But in particular, we're going to look for solutions that can be written in this way, right? Where kind of our temperature profile, we can, in a sense, decouple space and time, or say mathematically, we want to look for solutions that take this form where we have one function that depends on time times one function that one function that depends on space times one function that depends on time. And these two don't necessarily interact, okay? And so maybe thinking, well, it's quite a special form of a solution. Why not look for something more general? And our strategy will be, well, let's look for solutions like this, and then we'll kind of use the fact that this PDE is linear, so that if we have two solutions to all of this stuff right here, we can add them together and get another solution. And so instead of thinking of kind of this solution right here as, kind of the final piece, figure out what those functions are, we're done. Instead, what we want to do is think of these pieces as the building blocks for a general solution, okay? So yeah, that's the goal for these videos. And so, as I said, well, we're looking for building blocks. So what is the end goal? The solutions to the heat equation that we'll be working with a lot will look like this, okay? Where the building blocks are some constant times a function that only depends on x, so it's phi of x, times a function that only depends on time, this e to the negative k stuff times t. And then we add them all up and we produce our general solution. Okay, so that's the goal of these videos. Okay, so this technique where we're looking for solutions kind of that look like a product, this is called separation of variables, right? So if we assume that a solution takes the form u of x comma t is phi of x times g of t, right? What must phi and g be? Well, what do we have to work with? And we're working with the differential equation, so let's go ahead and differentiate. Take the time derivative, right? Only g depends on time, so time derivative of u only affects g. Likewise, if we take the spatial derivative of u, or the second spatial derivative, only phi is affected and not g, okay? But the PDE that we're looking at, right, this tells us how these derivatives relate. So if we plug all this in, right, to this PDE, then this is the expression that we get, okay? And so rearranging things, we're going to get, so here, bring this g of t and this k. Bring this g of t and k over here. Bring this phi over there. Okay. So we're going to get on the left-hand side, 1 over k, 1 over g times dg dt is equal to 1 over phi times d phi dx, or d squared phi dx squared. Okay. And so the observation is that, right, the left-hand side all of this only depends on t. So whatever function this is, maybe call it little g, this is just going to be g of t. Right? While on the right-hand side, that only depends on x, right? So maybe over here, right? So maybe this thing right here is equal to g of t. This thing right here is equal to, I don't know, h of x, okay? But we get that this thing g of t is equal to h of x, okay? So as we vary t, for example, right, whatever this function g is, it could change, right? Depends on t. But as we vary t, right, we're not varying x, and so h of x isn't changing, right, the function on the right-hand side, okay? So it tells us that this function h is actually constant, right, because it does not change as we change t. Likewise, this function g is also a constant, because if we move x, if we vary x, h of x may change, but g of t doesn't depend on x, so g of t won't change, okay? So one side depends on t, the other side only depends on x. So both sides must be constant, okay? And they must be equal to the same constant. So because we're working with this technique called separation of variables, we usually call this constant the separation constant, okay? And we're going to write it as minus lambda, okay? So right now, lambda can be any number. It could be positive, negative, 0. But we're keeping the sign just for ease of computation, okay? And we'll see why in a little bit. Right, so writing all of that out, right, we have constant is equal to this constant. And so then if we kind of pick the pieces apart, what do we end up with? Well, this left-hand side is equal to a constant, and this right-hand side is also equal to a constant. Okay, and so the utility here is now, instead of working with a partial differential equation, right, where we have kind of different kinds of variables showing up, now instead we're working with two ordinary differential equations. Okay, and ODEs we know how to solve. Okay. Right, so we can rewrite all of this. If we move things around, ignore the arguments, we get the ODEs in a slightly more recognizable format. dg dt is minus lambda kg. D squared phi dx squared is minus lambda phi. Okay. Okay. So so let's talk about the boundary conditions first, right, which we were given. And so remember that the boundary conditions for u were 0 at the endpoints. Okay. So if we plug in, right, so u at 0 comma t, right, phi is the only thing that depends on x, so phi of 0 times g of t is this thing here. And the boundary condition says that this is equal to 0. Okay. So what that tells us is that either phi of 0 is 0, or g of t is 0 for all t. Okay. And so right now, either option can happen. But notice that, well, if g is 0 for all t, right, so this function that depends on time, it's always 0, then our solution function will be identically 0, okay? So it's a solution, but it's not really doing anything interesting. And we usually call this a trivial solution, right? It's a solution, but it's not really giving us anything valuable. And so generally we care about non-trivial solutions, right? We want our functions to actually do stuff. And so what we conclude then is, well, it can't be the case that g of t is 0. We want a non-trivial solution. So the only other option is that phi of 0 is equal to 0. Okay. And likewise, if we look at the boundary condition for the other end, we get that phi of L is equal to 0, okay? So if we go back, right, the two ODEs we're working with is still the piece in time. So technically we have that initial condition, right, which tells us the profile at time equals 0, but we're going to wait until we've worked with all our building blocks and put them together and then incorporate the initial condition. So that's the function for time. And then the other piece is a function for space, right? So here we have this, right, same ODE here, except now we have these two essentially boundary pieces of boundary conditions or boundary information. But we have these two pieces of information for the second order derivative. And so we have enough to specify kind of what that solution is. Okay. And so the initial condition for G, which comes from U of X 0 is equal to F of X, that we'll deal with later. Okay. But we can start to solve these ODEs, right? So for dg over dt is equal to minus lambda kg, we can rewrite it a little bit to get dg over g is equal to minus lambda k times dt. Integrate both sides, we get log of g is equal to minus lambda k t plus some constant. And then taking the exponent of each side and kind of moving this constant in with whatever, we can write g in this form, okay? So what this tells us then is, right, these building blocks of kind of these product solutions, right, the piece that depends on time is going to be exponential, okay? And so again, right now, lambda can be anything, but especially if lambda is positive, k is usually positive, is pretty much always positive for our situations. But anyways, if lambda and k are positive, right, time, think of it as increasing, right, starting at 0, going off to infinity. So what this shows is that this term here, as t goes to infinity, as time keeps increasing, this whole thing will go to 0, right? So the time piece in our product solution, that will decay to 0, okay? And so that matches with our intuition that, right, especially if you, right, whatever initial profile, temperature profile you have, if you say the ends have to have 0 temperature and you let the heat flow for a while, right, what you might expect is for the equilibrium solution, you're going to have a straight line, right, straight line connecting 0 to 0, okay? So your end temperature should be 0, which we're going to get from this exponential piece. Okay. Okay, and so then the other thing as well, right, the C is just some to be determined constant. The initial condition will is enough information to essentially figure out what C is. Okay. Okay, so then kind of the next main question is, well, what are the possible values that this thing minus lambda can take? Okay. And so it's a computation, but we'll talk about that here in the next part.